When looking at systems, we can encounter the same difficulty we encountered earlier in the course when we had a non-homogeneous solution that involved a differential family, but there was something in that differential family that was already in the corresponding homogeneous solution. And the solution, fortunately, is also the same here. We take the function that we'd like to include and multiply it by t. Again, we multiply it by t or t squared or t cubed, but in most applications, 1t suffices to avoid the overlap or to eliminate the overlap. The only wrinkle is that we would also include all lower multiples of t in the assumed form as well. We didn't have that in the previous solutions. And the reason we need that is because there's vectors involved and we might have different vectors with the same function. Let's consider that approach in the context of an example. So we have here again a non-homogeneous part to a differential equation system. The first thing we would do when faced with this question is take a look at the homogeneous portion of it and figure out what that solution is simply by looking for the eigenvalues and eigenvectors of the matrix A. And then we could start building our solution as C1, here are those eigenvalues and eigenvectors, e to the eigenvalue, t times the eigenvector, plus a constant e to the eigenvalue times t, minus 1 times t, times the constant eigenvector. That makes up our solution to the corresponding homogeneous case. Then we would say, let's add something to do with the non-homogeneous part. The differential family is straightforward here. It's simply e to the negative t, because it's the only function, and if we differentiate it, we get the same function back, so we don't need any further members. However, we have that warning sign that it's in xc already. And if that's the case, we'll do exactly what we just proposed as the solution. We'll take what we need, e to the negative t, and we'll multiply it by t, and that'll make it linearly independent or distinct from what we have already, times u1. So there's some vector of constants. And here's this new function required because of the overlap. With the corresponding homogeneous solution. However, we don't stop there. We also include the original function e to the minus t times some other vector of unknown constants that we would solve for. And all of that together would make up our non-homogeneous part of the solution. And we would find u1, u2 by subbing in that part of the solution into the differential equation. So nothing new there. The solving, though, gets pretty ugly pretty quickly, so we're not going to go through the details, and we won't ask you to do it for this kind of repeated case, but it's important to know the kind of form we get. It's especially important to know it when we see the next example. Here we have another non-homogeneous differential equation, homogeneous case here, matrix A, plus some sine waves on the right-hand side or in the non-homogeneous part. Again, we're pre-calculating the eigenvalues. So here are the eigenvalues. And we've pre-calculated the eigenvectors here. And what can we do with those? Well, we can build our xc solution here explicitly. And looking at the values, we have an a or an alpha, that's what we called it in our earlier formulas, and a beta here, and those go into the exponentials and into the frequency of the sine and cosine terms. Same thing for the sine and cosine and the exponential here. So what we get is a pure oscillation with constant amplitude for our corresponding homogeneous solution. Now, let's take a look at what happens when we include our differential family for the non-homogeneous part. Well, the differential family is going to be sine of bt, that's given already, so it's definitely in the set. And we're going to need its cousin, its friend, cos of bt to complete possible derivatives. So if we have those two in our differential family, what we would get is a non-homogeneous solution that looks like sine of bt times u1 plus cos of bt times u2. And then we would solve for those vectors u1 and u2. However, that's only going to be if that b value is not equal to 2. As soon as that b value is 2, then we get overlapping solutions. We get sine 2t, cos 2t are in our corresponding solution already, and that would mean we would have to boost by t. We would have sine, here's the specific case, 2t, then we'd have to multiply that by t to avoid the conflict or generate a solution that's different, and times u1, plus, again, t times the cos of 2t, times some other vector u2. And then we'd also include the bare bones versions with their own vectors. There we go. Why is this relevant? If we think back to the kinds of systems we've looked at physical systems with springs that gave us these kinds of equations, gave us these kinds of eigenvalues and eigenvectors, particular complex roots. And so, if we have an external force, guess where it's going to show up? If we're modeling physics, it's going to show up in this non-homogeneous part. So this would be where F external would be in the spring mass system. It's going to cause us to have amplitudes that grow linearly over time as soon as we have that overlap between the non-homogeneous part and the natural solutions or the corresponding homogeneous solutions here. So all the same themes we've seen with resonance come in here with systems as well. Just to restate that again, if the non-homogeneous part has a sine or cos with exactly the same frequency, as the XC, then we're going to have all the properties of resonance, which is our T sine and T cos in our non-homogeneous part of the solution. Key thing being those T's. If it's merely sine and cos with close to the same frequency as in the corresponding homogeneous solution, then we get what we saw earlier, beats or large amplitude response. Not infinitely growing like the resonance ones, but still very, very large oscillations at the end of the day. Again, we're just trying to restate that theme. External forces which vibrate, which have frequencies and periods. If there's exact matches, we get resonance. If there's close matches, we get large amplitude responses, not infinite, but large. And these are the kinds of things we either worry about or actually aim for, depending on the application, in terms of designing the relationship between external forces or external signals and the natural behavior of the system when it's not being forced or being pushed on. The concept's exactly the same as what we've seen earlier, it's just now in a slightly new mathematical form with these first order systems.